Good afternoon. In this video, I'm going to show you the derivation of the sine rule. So as you're already likely familiar with trigonometry, over on the right here, I've got the trigonometric identities that we use in right-angled triangles. And down below, I've got the formulae for the cosine rule. So the cosine rule being a method in which we can analyze non-right-angled triangles. So jumping straight into it, consider I've got a non-right-angled triangle, and not quite like that. I've got a non-right-angled triangle that looks as such. And notice that because it's non-right angles, I can't really use these trigonometric identities over here just yet. So what I'm going to do is I'm going to partition this non-right angled triangle into two smaller right angled triangles. So I'm simply drawing this red line such that it intersects or interacts with the base of the triangle at 90-degree angles. And I'm going to label or annotate this triangle using the non-right angled triangle convention. So let's say that the left-hand angle here is angle C, and thus the opposite side of that angle, we'll call that little c. Then I'm going to label the right-hand angle as A, and thus the opposite one as A there, little a, and finally we'll have angle B at the top, and we'll call the smaller one at the bottom little b. Now there are a few more features that I'm going to annotate on this triangle, and it's going to give me the names that I can use or attributes that I can use to get to the final form of the cosine rule down here. So the first I'm going to add is this red line here. I'm going to call it T. So the red line is of length T, and on the right hand triangle, let's say I'll draw the angle in there, the adjacent side, I'm going to say that is of length R. And because we know that the adjacent side on the triangle with the angle A in it is of length R, then we can say that the triangle with angle C in it is of length B minus R. Now, to get started in deriving the cosine rule, the method in which I'm going to do it is, firstly, I'm going to use the sine rule to derive a rule or derive an equation explaining the length of side T here. Then secondly, I'm going to derive an equation that explains the length of side B minus R down here. Then thirdly, I'm going to derive another equation using Pythagoras' theorem to explain the length of all of these sides in the right-hand side triangle that has angle A in it. So jumping into it, I can say that sine of theta equals the opposite over the hypotenuse. Now I always like to write this out because I get confused if I don't set it out in this form to begin with. Now I want to solve for the opposite. So what I'm going to do is I'll say the opposite equals h sine theta. Then I'm going to sub in all of my values. So the opposite in this case is equal to t, and the h in this case is side A, and it will be sine, wrong one. It will be sine C. So this is equation 1. Now equation 2, I'm going to derive an equation that explains side B minus R. So what I'm going to say is the cosine of theta equals the adjacent over the hypotenuse. Arranging for the adjacent, it is adjacent equals h cosine theta. And then substituting in the values, we have b minus r equals the h, when we said the h was a cosine c. Awesome. And I'm going to rearrange it ever so slightly, and rather than saying b minus r, I'm simply going to say r is equal to b minus a cos of c. Great. So what we've got here is the second equation that we're going to use. Now the final one is I'm going to write it such that I can derive the side lengths of the triangle on the right here, so containing angle A, in terms of Pythagoras' theorem. So c squared equals a squared plus b squared, or the hypotenuse squared, is equal to one side squared plus the other side squared. So simply writing it out again, what we're going to get is c squared equals a squared plus b squared. And in this case, our c squared is simply just c, so that doesn't have to change, which is nice and convenient. But our a and our b, we can explain that as t and r. So what was c squared up there? So we don't have to change anything, but a squared, that's going to become t squared, and b squared is going to simply become r squared. Awesome. Now notice we've already got t as the subject in this equation and r as the subject in this equation here. So we can simply substitute in a sine c all squared plus b minus a cos c all squared as well. Now breaking open those brackets, we're going to get a squared sine squared. Notice the location I put the squared, and then notice we've got two terms within the brackets, so I'm going to have to expand this out. So we'll get b squared minus 2ab cos c plus a squared and cosine squared of c. Great. Now I'm going to rearrange this to put it in a form where we can do a little bit more work, because clearly we can see we're not in the form of the cosine rule just yet. So what I'm going to do is I'm going to write a squared equals sine squared c plus a squared cosine squared a minus 2ab cos c. And I forgot the b squared, we'll just squeeze it in right there. Awesome. Now there's one trigonometric identity that we need to use to simplify this down even more, and it is sine squared theta plus cosine squared theta is always equal to 1. So 1 equals sine squared theta plus cosine squared theta. So put it in your calculator. For whatever value of theta you put in, it's always going to be equal to 1. So using this identity here, I can rearrange the formula above such that it becomes, factorizing for a squared, we've got sine squared c plus cosine squared c plus b squared minus 2ab cosine c. And using this identity that I've written in green, it will simplify down to, so everything in these parentheses here is going to simplify down to simply 1, which becomes a squared plus b squared minus 2ab cosine of the angle C. And all of that is equal to C squared. So it looks a little bit like the mix-up between Pythagoras' theorem, this form here, and a little bit of some cosine and some factors in there. So what we can see is we've got form 1 over there, so highlighted in yellow. Over here is the form over here. Awesome. Now, using some simple rearranging, I'm going to show that we can go from this form, so finding the length of a side, to being able to find the length of an unknown angle if we've got the lengths of 3 different sides. So, rearranging once again, we want to rearrange in terms of C. So what we're going to get is, moving the a squared and the b squared to one side, we're going to get 2ab cos big C, and that will be a squared plus b squared minus c squared. And I'm going to divide both sides by 2ab and take the inverse cosine. So divide first, and we will get a squared plus b squared minus c squared all over 2ab. Then jumping down to a new page, we're simply going to get the angle C. I'm going to take the inverse cosine. So not to be mistaken as 1 over cosine, it is the inverse cosine function we are using here. Inverse cosine of a squared plus b squared, minus c squared, all divided by 2ab. So, highlighting this in teal, there we go. So, we have the derivation of finding an unknown angle in the teal over here. So, going back to prove the cosine rule, I drew a non-right angled triangle. I dissected it or partitioned it into 2 right angled triangles, and then I used the right angled trigonometric proofs or ratios to find the opposite and the adjacent side, and then I substituted those equations into Pythagoras' theorem. Use this formula here, or this identity here, 1 equals sine squared theta plus cosine squared theta, and thus I arrived at c squared equals a squared plus b squared minus 2ab cos c, and then rearranging again, I arrived at the angle C is equal to the inverse cosine function of a squared plus b squared minus c squared all over 2ab.